Swayam Prabha. Digital India. Educated India.
So today we will discuss the data structure augmentation. So given some problems, how we can search for a data structure. So there are few methods to do that. One method is we can think for a totally new data structure for this, or we can we know some good data structure, so we can take one of that data structure, underlying data structure, and then we can do some augmentation there. We can introduce some field there for our problem. So for different problem, we have to introduce. We have to do the different ways of the augmenting that data structure. So that is the idea. So given some problems, we need to find the data structure. So instead of having a data structure from the scratch, we can take some underlying good data structure. Then we can do some we can add some extra field over there, which will help us in our problem, to solve our problem. So that is called data structure augmentation. So today in this lecture we will discuss two problems. One is dynamic order statistics problem, and second one is interval tree problem. So let us start with the first problem, which is dynamic order statistics. So we have seen the order statistics problem. What is the problem? Problem is we have given some numbers, we have given some keys in a typically in an array or some way, and then we need to find the ith smallest element. So I is also part of the input. So so that was the order statistics problem we have seen. If I is 1, that is minimum. If I is n, that is maximum. If I is n by 2, that is called median. So we have seen some algorithm based on our partition code, and then we have seen the worst case linear time code. There we partitioning the group, and in order to get the good pivot. So those things we have discussed in our previous lectures. So that is called order statistics problem. But that set is static. We have given a set. That set is not changing. I mean,
So
we are
are
not.
you screen because it's not visible?
Is it coming to others?
Yes, sir, it's visible.
Yes, sir, it is visible.
You can see it, the screen?
Yes, sir.
Yeah,
Then it must
maybe.
come from my end.
Yeah. Maybe you can just log in and log out and log in, and then you are getting the presentation, right?
Yes, sir, we can see the presentation.
Thank you. Okay, so that set was static. That means we have given some numbers, we have given some records which key values are given, and we need to find the ith smallest element. We need to find the I is also part. That was the order statistics. But here the more challenge is, if we allow this set to be dynamic, that means if we have to do the insertion and deletion from this set. This is the set S, where we are storing this key values. So this S set is, earlier in our earlier lecture we have discussed this, where S set is static. We have given some keys, we need to find the ith smallest element. But here the more challenge is, this set S we want to be dynamic. That means we want this somebody should join this set, and we should able to delete somebody from this set. So that is a dynamic set. So that is the challenge now. So on that case, we have to think for a data structure which can help us for this dynamic set S, and which should able to perform this operation, search like get the ith smallest element. At some point of time, there are n elements, n keys are there. So we want to find the who is the ith smallest element, who is the median of this set, who is the maximum of this set, who is the minimum of this set, I is equal to 1, who is the n by 10th smallest element in that set. So at any point of time. So that, but the challenge is this set is dynamic. So, and also this problem OS rank, like this order OS means order statistics. This is a problem where we have given a key, we know the key is there. So we want to find the position of that in this set. That means the rank of that element. Rank we have defined. Rank of an element means If we sort that set, then the position of that element in the sorted array. So that is the rank of an element. So these two problems, we will mainly concentrate on this problem, select, OS select. Okay, so how to, so we need to suggest some data structure for this dynamic set S, so that we can perform this operation in a faster way, so that we can do the select in a faster way, so that we can get the ith modest element in a faster way. Yeah, so this set is dynamic. So we have seen some dynamic data structure, which some data structure which can handle the dynamic set of records, dynamic set of keys. And we have seen one good data structure in the last lecture, that is a red black tree. So we want to take the underlying data structure as a red black tree, and there we want to do some augmentation there, so that it will help us to solve this problem. It will help us to search, I mean for our problem, select problem. So that we'll see. Yeah. So basically we use the underlying data structure as a red black tree, where the keys are the nodes. This is one node, and this is the extra information we are putting in this node. So that is the augmentation we are doing over here. So why this extra information we are introducing, how it will help us, that we will see. Okay. So what is the size? We are keeping one information, the size information. Size of a node means the size. So this is a tree, red black tree. So consider a node X. So here we want to have another information. What is that? Keep the subtree size of this node. So we want to keep. So this is a tree, subtree rooted at this node. Root is there. So this could be root also. This is a tree. This is a tree, subtree rooted at this node. So we want to this is the size, means the number of nodes in this subtree, basically, other than those nils. Number of nodes in this subtree. So that is that information we are going to store in this node in the size field. So our node has increased one field, that is we are introducing another one extra information there, that is called size of the subtree rooted at that node. That means the number of elements over here, number of elements in this subtree. So for root, the total number of elements, and for nils it is 0. Nils means the new leaves we have introduced in the red black tree. So that is the extra information we are introducing over here. We'll take an example, then it will be more clear. Okay, so this is, suppose this is our key values M, C, A, F, like this. So these are the key values. We have some records whose key values are these alphabets A, C, M, F. Okay. Now we form the red black tree. This is a binary. So red black tree is a binary search tree. So if we check any node, it's greater than from its left subtree. So B, alphabetical ordering. So D is less than F. So D is in the here, like this. So you can easily verify all the nodes which are in the right subtree are greater than. Greater than means alphabetically greater than, here we are considering. P is greater than M, like this. Okay. So this is a binary search tree. Now we have to color it. I mean, the nils are hanging over here. So there are nils over here, nils are hanging over here. Now we need to color the node in order to get it, in order to say this is a red black tree. So can you suggest some color, quick coloring on this? So we know this should be black. Red is root is black, and all the nils are hanging over here. All the nils are black. All the nils are the new introduced leaves. They are all blacks, and we need to color this node so that it should follow all the properties. So any suggestion of the coloring?
So C and P red, A, F, N and Q black, and DH red.
We want to make this to be black. And what about this? This cannot be red. This has to be
Black, sir.
black.
Black.
Yeah. And then what about this two?
N and Q black.
This is black. This is also black. And
D
what
and
about
H
DH? This
red.
will be
Red.
red. Yeah. So can you just quickly check whether it satisfies all the property? Like one property was that if a node is red, then the parent is black. So that is satisfying. We can even quickly check the black height. So black height of this node is 1, 2. Nils are there. Nils are black. So 1, 2. Here also 1, 2. So that is fine. So for this node, if you consider yeah this way, fine. So fine. So this is one coloring. This may not be unique. Even I know there are one other possibilities over there. You can change this to be this. This is red. This is black, and then this is anyway. You try that. Okay. I know there are other possibilities are there. So this is a red black tree, our good friend. Okay. Now this was the original tree. Now we want to introduce another field which is called data field, like sorry, which is called size field. So we want to introduce size of each node. Uh, that means the number of nodes rooted at that node. So that is the size. So size of Nils are 0. That is we are defining. So size of Nils are 0. Now what about the size of this node? So Nils has so size is basically this formula. So size of a node X is nothing but, if we consider a node X, so this is the left subtree, this is the right subtree. Anyway, we don't know which one is bigger, and we have, so size of this node is nothing but how many nodes, how many nodes are here. That is the size of left X. How many nodes are here? That is the size of right X, and plus the node itself, the X. That is the formula we will use. So that is the formula. That this is basically the number of nodes which are hanging in that tree, rooted at that particular node X. So for that, so here what is the size of this node? So number of nodes rooted at this tree. So size, the Nils we are ignoring. Nils has size 0. So this is basically size 1. This is also size 1. Now consider the size of this node. Now size of this node, is nothing but size of left. Size of left is 1. There is only one node over here. Size of right is 1. 1 plus 1, 2, and plus this node itself. So 3. So there are 3 nodes hanging in this subtree rooted at this node. Similarly, this node, similarly size of A is 1 here, and this node size of left is 1, size of right, we can just check this field, this field 3. So 1 plus 3 is 4, plus size of this 1 plus this node itself, so 5. So this is the size of the tree, subtree rooted at this node C. Total 5 nodes are there, like this. So similarly we can this node 3, and then finally we can make the size of root, size of left subtree. There are, we can check this field only. This is 5, and this field is the size of the right subtree. This is 3. So 5 plus 3 is 8, plus 1, 9. So this is done. So this is the extra. This is the augmentation we are doing in our red black tree. So now why we are doing and how it will help us, we'll see when we go for the this. Why this size is important for our case. I mean, we are trying to get the ith smallest element. How the size is important in terms of ith smallest element. Yeah. So before that, can you just tell me how this how to get the ranks of this element? How to get the rank of this 9, say? Any idea how to get the rank of this 9? Rank, you know, no? Rank means the position of that element in a sorted array. And we are looking for ith smallest
Size of
element.
left 3 plus 1.
Yeah. The rank of this is basically size of left plus 1. Why? Size of left is 5 plus 1. That means the rank of this element is 6. Why? Yeah, you're correct. So rank of this, if rank we defined as k, rank of this element is size of left we can get it from here, which is 5 plus 1, so 6. Why? My question is why it is true.
Sir, BST is similar to the partition algorithm. So all which are smaller are to the left of the node, and all which are greater to the right. So it is at the correct position.
Yeah, so because this is a binary search tree, we know binary search tree having the property, if you consider any node, then then that node, all the elements which are in the left subtree will be less than that node, and all the elements will so that means if we call the partition, so x will be in correct position, so x will be sitting here, this is our x, and all the elements which are left subtree will be less than x. This is basically our partition. So that means the number of elements over here, that we can get it from here, that is the size of the left subtree, and then plus 1, that is the rank of the element, that is the because when we call the partition, x is in correct position, we don't need to do anything on the x. Only thing for quicksort, we have to call quicksort again here, again here, anyway. So yeah, so correct, so that's why we are looking for the size, we are maintaining the size so that we can get the rank of this element. Now suppose we are looking for ith smallest element, suppose I is 6, we can easily get the rank of this root. If the root is 6, if the rank is same as I, we return happy day, but always we may not have a happy day. So suppose we are looking for 5th smallest element, then what to do? Any suggestion? This is also a recursive call.
Sir, the size, the rank equal to size of left plus 1 is only valid for the root node, right?
No. For what about, yeah, for the root node here, yeah. So now suppose we are looking for 5th smallest element. So this is a divide and conquer technique. We are discussing the algorithm now. So suppose we are looking for 5th smallest element. Now we know the size of this is, rank of this is 6. We are not happy. So we need to search further. We need to divide this problem into sub problems. So this is the rank is 6, but we are looking for ith smallest element. So what to do?
We go to the left child of the
Go to the
of
left.
that node.
Yeah. So the similar way we did for the select, we have to go for the one part of the array, but here there is no array, only the tree. So we have to call again the west select in the left part of the tree. Okay. For this left part, this is again this is a tree rooted at this. So we'll do that. Similar way we'll continue. So let me go to the code here. So this is our west select pseudo code. So we have formed the tree. We have the tree, and that tree is our red black tree with this extra information, with this augmentation is size we are maintaining, the size of the every node. That means how many nodes are there. So okay, now this is the code. So now we just start with the root. This is our root x. So you can just have t also, the tree you can just insert, or root. If root is null, if there is nobody, we just return. Otherwise, we just calculate this size of left plus 1, that is nothing but the rank of that element, rank of that node root. Now if rank is I, if we are looking for the ith smallest element, which is the k basically rank, we return happy day. If not, if I is less than k, then we have to go for the left part. So if this is our root, and this is the left subtree, and this is the right subtree. We know all the elements over here are less than x. We know all the elements over here are greater than x. This is the divide and conquer technique. So now rank of this is k. Now suppose we are looking for ith smallest element, which is less than k. Then we have to look for the ith smallest element in this subtree. Again, this is a new root over there, and again we do the same thing. And for this root, new element, always that is there, that rank of the element is the rank of that root is the size of the left subtree plus 1. In that corresponding Yeah, you are correct, in that corresponding subarray. Okay. So again we call this wave select, and we will do that. Okay. So, and if we are looking for ith smallest element which is greater than k, then we know we have to go for the right subtree, but with the new I, because we have already come across with the kth smallest element. So now we need to find the I minus kth smallest element only in the right part of the tree. So this we know. So this is the divide and conquer technique in this dynamic setup. Okay. So this is the code. This is the code, pseudo code for our wave select. Any question before we move? So we can take an example. Suppose this is our given tree and we know the color. We have already given the color. Now suppose we are searching for fifth smallest element. I is equal to 5. Okay. Now we can have the rank of this element. So rank of this element is 5. Sorry, 6. Yeah. So rank of this element is 6 because this is the 5 is then the size of this left subtree plus 1, 6. But we are looking for fifth smallest element. So that means we have to again go for the further call on this. So that we do. So we go for the left part. Again we calculate the rank of this node in this subtree, in this tree, not the whole tree. Okay, we don't need that. So rank of this node is again the size of the left subtree in this part only. So that is 1 plus, so rank of this node is 2, but we are looking for fifth smallest element. So we have to go for right part of this tree. So again the recursive call. So again we have to find the rank of, so this is our new root. Okay. So this is a recursive call. We are calling wave select again and again until we reach to a nil, or until until we reach to a this will match. So now rank of this node is this size is 1 plus 1, 2, but we are looking for third smallest element. So again we have to go for the right part of this. So right part we have this node. So rank of this node is, and with the right part how many? I minus k. So I minus k is 1. We are looking for one smallest element, and there is only one element. So even the rank of this is 1. So we got the fifth smallest element. So fifth smallest element is h. So that is the execution of this wave select on this example. Okay, so this is simple example. So now what is the time complexity for this? If we maintain the red black tree, we know red black tree is a guaranteed height balance tree because the height is log n. And so what is the search time? What is the select this code will take, because it is the height of, worst case it will go to the height of this tree. So it is a log n time algorithm, this wave select. Okay. But only thing we need to check the this dynamicity, like this is our set S. S contain these elements. So we need to check how we can maintain this, because we have introduced a new information, the size. How we can maintain this size in a dynamic scenario. That means when we whether we can maintain this in the same time of that operation insert and delete. That means order of log n. So that we have to see. Okay, now one question is why to keep the size? Why not to keep the rank itself? Because we are maintaining the size. If we come back here, so we are maintaining the size of each node, right? So instead of that, once we get the size of this left, then we can maintain the. We know there are 5 elements over here. Then rank of this is 6, so we can easily have the rank over here. So rank of this is 6, so we can easily, instead of calculating this, we can easily have this if it is I is 6 or not, so that we can do. So the question is, why don't you put the rank in our argumentation instead of size of that? Any idea?
Sir, for that case, suppose that we are inserting some element which is pushed in some left subtree. So then for that we have to update the ranks of that subtree also, and we have to update the ranks of the right subtree also. So it will take some much time. I mean,
Yeah.
uh,
Yeah. Yeah. So suppose we are inserting a new element which is a minimum, which is minimum among all the existing elements. So so if we insert a minimum or maximum, something like that, then the rank will change for every element. So that will cost us order of n time. So we have to change the rank of each of the elements. But to maintain the size, I'll come to that. Size is easier to maintain because when we insert it, we just need to follow that path and we change that field. But to maintain the rank, if we insert a minimum among the all the existing one, then we have to, so rank will change for every element then. So we have to change the rank for all the n elements if there are n element in that. So that is that is not possible. I mean, that is difficult to maintain in the here. Okay, now we'll consider this modifying operation, how we can do the insert and delete. So specially we know the insert and delete for red black tree, but here we have one bit of information extra, the size. So how to maintain the size in the same time complexity, because insert we know insert will take order of log n time. So whether this if we want to maintain this size, whether we can do it in the same timing or not, so that is very important. So that is called whether we can update this size of the left subtree with the same cost of insert and delete. So that is the thing. If we need more time to maintain this extra field, then there is no gain. You understand? So we need to do that in the same timing. So that is very important. So that we'll see how we can maintain this extra information in the same. So let us take an example. Suppose you want to insert a new node k. So what is the binary search tree red black tree insert? First we have to insert in a BST. So we insert in BST. So we check k with the root. K is less than this. We have to insert in the left part. Again we check k with the So this is the BST insert. We need to check k with the this node. K is greater than, we have to go for the right part of the tree. So this is recursive call until we reach to a nil node. So again we need to check with this. Again k is greater than f, we have to go here. Again k is greater than h, we have to go here and we insert there. We insert k over here. Now how to update this size? Now once we insert k, then we have to we know size of this is 1, and similarly size of this will change now, the parent of this. So this is 2 and this will also change. So this is we will have only change in the path wise, but if we maintain the rank there, we have to change all the elements. So that is, as you said, in left part and right part also, but here we are only maintaining this size in this path, and that is also log n time. But the question is how to maintain this, because for red black tree we know once we insert we may need to do, if we have to do only recoloring, that is fine. We know that we put the color to be red, because if we put the color to be black, then it will hamper the black height. So we put the color to be red, and if this is black, we are done. But problem is if this is red again, then we have to do some rotation operation that we have seen in the last class. So that rotation operation whether will cost us in the maintaining this size, to fix the size. So that we will see. So let us take this example. Suppose we have a portion of this tree. So these are the size over here. So this is a node and this is left subtree. If you remember, we have two nodes and we do the right operation, right rotate. So we want C up, E down. Okay, and these are the tree. These are the size of this left subtree. These are the size of this right subtree. We want to see how to maintain this size in the rotation operation. So if you do the right rotate, C will go up and E will come down. So this is alpha, this is beta, this is gamma. If you remember this operation, so alpha will be hanging over here and beta and gamma will be hanging with this node, and we are changing some pointers over here. Now how to maintain this size over here? So size of this will unchange alpha. Now size of beta will C, size of gamma is 4. Now size of this will be the size of this plus 1, and then size of this will change, and nothing will change in the up, right? So only few, only 2-3 size are changing. So that can be handled in order of 1 time. So that is very important. How to, because this rotation is required in order to make this tree again to red black tree. So whether this size can be maintained in the same cost of the with that. So size can be handled in the order of constant time. So that is a good news. So similarly, for left rotate, if you want to make this up, this down, this up, similar way. So the insert and delete with this new extra information can be handled in order of login time.
Sir, how did E become 8?
Which one? This one?
Sir, on the right side, E became 8, right? How did it happen?
Yeah. So if you remember the rotation operation, so this was we referred as alpha. This was we referred as gamma. This is a subtree. Subtree alpha is one representative. Sorry, this is beta. This is beta, and this is gamma. So for our rotation, we know this alpha will be hanging over here, and this is beta, and this is gamma. So how many elements? 3 elements over here. This is beta and this is gamma. So 3 elements over here in this subtree, 4 elements. So this is the size. I mean just the size of this. This information will get from this node, and this is the size. So now what will be the size of this? Size of this will be size of left plus size of right plus 1. So this is size is 3. So 4, 7 plus 1, 8. Similarly, size of left is, this is alpha, number of elements is 7 over here, and 7 plus 1 is 15 plus. Is this your question? I mean, we just want to see how extra time we are spending to maintain this size, because this E was 15, now E came down. So E was 16. That means the number of elements over in the tree subtree rooted at E was 16, including E. But now E became down. So now we need to get the size of E. So size of E, how we'll get? Size of this alpha beta, size of gamma, which we know 3 and 4 plus 1. So that change we can easily do. So just a few size changing. Is this okay? We need to ensure that this will not cost us more than constant, because this is just a same thing, the pointer changing, which we have to do in the red black tree rotation. Okay, so this is the general methodology for data structure augmentation. So one example we have just now seen is the order statistics tree. This is we have seen, but in general, so we given a problem, if we want to use some data structure and with some augmentation, what is the technique we choose an underlying data structure. In our example, we have taken the red black tree, which is a very good friend because it's a height balance tree. Then we have to introduce the additional information there, like in the node. Here we have maintained the size. Okay. So additional information we have to maintain, and we have to verify this additional information can be handled. This is the third step. Can be handled in the dynamic scenario also with the same cost with the insert and delete. Because otherwise, if we spend more time in handling that size, then we cannot afford that. We have to maintain this extra information with the same cost, like in linear time of the insert and delete. Okay. So for there we need to check the rotation, because we are using red black tree. We need to check the rotation, whether rotation to maintain the size, whether rotation in the rotation we are doing extra work or not. Then we have our operation like OS select, OS rank. OS rank is also similar. We need to maintain the we know the, if we go to that element, we know the rank of that element for the left subtree, right subtree. Then anyway, I suggest you to we are not discussing OS rank here, but you can easily, this is there in the Codeman book. Okay, now let us go for the next problem, which is called interval tree problem or interval search. Now what is the problem? Problem is, here is also the set is dynamic. We have given some set of intervals. So here we have a set which consists of some intervals, time intervals, some close intervals, say 5 comma 5 comma 11, then then 4 comma 8, something like that. So this is one example, 4 comma 8. Yeah, dot dot dot. We have here some intervals, time interval. So this is the set, and this set is dynamic. That means at any point of time and any interval can join this set, and any point of time and any interval can get deleted from this set. So now what is the so we want to have a query. What is the query? Interval query. That means given the interval, suppose we have given this I interval, I is 7, and we have this set S. S is having, say, this interval 5 comma 11, 4 comma 8, 17 comma 19, 15 comma 18. These are the interval at some point of time. Okay. Now what is the query? Suppose we have a query interval. We have given some I interval, and we want to see whether is there any interval which is overlapping with I. So for a given query interval I, say I is here 7 comma 10. This is our query interval. 7 low of I, that means low endpoint is 7 and high endpoint is 10. So we want to see whether we want to get only one interval. Suppose we want to get one interval which is overlapping with this interval. So what is the interval which is overlapping with this? I mean, the intersection is not null. So 5 comma 11. So we can return 5 comma 11. That is we are looking for, or we can return 4 comma 8. Only one interval. We want to return only one interval. But if the interval is like say if our I is say 26 comma 30, if this is our I query interval, then there is no interval overlapping with this. If S is this set, so we'll say sorry boss, there is no interval overlapping with this at this moment. That is the problem. The problem is clear. We have given some set of intervals. This set is dynamic. So for example, for the timing we have this 5 comma 11 one interval, 4 comma 8, 17 comma 19, 15 comma 18, 22 comma 30, 23. So these 5 intervals are there. Now we have given a query intervals, say 7 comma 10, and we need to find an interval which is overlapping with this. We are happy with only one interval. If there could be many. We'll see how to report all the intervals. So we'll see that. First, let us take the problem, easier problem, like whether there is an interval which is overlap with this. Okay, so any suggestion how we can handle this problem? Any data structure can you suggest to handle this problem? You got the problem. We have given some interval, say to them this is some time interval, 1D intervals. So now we have say suppose there are n intervals at some point of time, and this set is dynamic, and we have given the intervals. What is the naive approach? What is the naive approach? How to get an interval which is, what is the naive approach? Any idea? If there are n intervals, we can search it, we can check, we can start with one interval, and we can check whether they are overlapping or not. Just we can check the low end point, high end point of this interval and with the query interval. If not, we will go for another interval. If not, so this will take us linear time. So we'll check each and every intervals like this. So this will cost us linear time, but we want to do it something faster way than the linear time, logarithm way. So for that we will do the data structure augmentation. So for that we need to take some underlying data structure. Again we are going to take the red black tree, our good friend, and we'll take the red black tree, and how we'll store the interval there. So we'll key the node red black tree key on the low end point. So low end point will be our key value. So we'll have a node over here. So if we have an interval say 5, 11, so we'll store this interval in this node and we'll put 5 here. So our keyed this node, I mean red black tree key on the low end point. So this is 5 like this. And here we are going to have a maximum field. What is the maximum? Maximum means we have this tree. Now whatever is the maximum value over here in this subtree rooted at this, so that we are going to store over here. Maximum means including the intervals. So here in this interval, what is the maximum value? 11. So if there are no points which are having more than 11, so this max will be 11. So that is the extra information max field we are introducing in each of the node. Is this clear? So let us just have this. Yeah. So we are putting this interval in a node in the red black tree where we are keying this as a left end point, and here this is the m is the maximum largest value in the subtree rooted at x as well as the interval itself, okay, corresponding to that key. So that is the extra information. We will take an example, then it will be more clear. So we had that those intervals that set S. Now we are going to form this red black tree. Now we are key valued. This is a node whose key value is 17, and this is a node 5, 11 interval, and the key we are making this key as 5 because we have to maintain the binary search property. That means the key value of a node must be greater than from all the key value of the node from the left part and must be less than all the key value of the node. So that we have to maintain. So for that we need to have a key value. So key value of this node is the basically left end point of this node of this interval. Okay, so if we just check it, this is a binary search tree because all nodes, if we consider this node, left subtree is this one whose key value is 4, 5 is greater than 4. Again right subtree is 15 and 7, 5 is less than all this. So you can easily verify this is a binary search tree, and we have nils over here hanging, and you can color these nodes. So root are black, nils are black, and you can make these two to be red. Again I am telling you this is not a unique coloring, even you can change these to red and these all are black, or this is, yeah, is this the color is okay, yeah. So you can just change these to red and these to black, that will also work. Okay, so now this is a red black tree. We have nils over hanging here, nils are all blacks. This is a red black tree. Now only thing we need to check this augmented field. I mean we need to maintain this field like max field. So what is the max field? Max field is we want to put the value over here so that this will indicate the maximum value in this maximum value in this tree rooted at here. So this is the root. So what is the maximum value rooted at here? So that we want to put it here. Why we want to put it here? We'll see. I mean because we want to search the interval. So we'll see that how it will help us. Okay. Now what is the formula for this max? So max will be the max of the left, max of the right, and the high. This is the interval. So there is a high the high of the interval, the end point, low end point, high end point. So among these three, whichever is the maximum, whether max of left, max of right, or the the high end point of this interval. Among these, whichever is the maximum, that will be our this field. So start with this node. This is there are meals only. So max is 10. So we put 10 over here. Now start at this node. So formula is this. So what is the max at left? 10. There is nobody in the right. Only nils are there. And this is the high end point, 18. So max of 10 and 18 is 18. So we'll put 18 over here. So that means, what is the meaning of that? That means 18 is the maximum value rooted at this subtree. Rooted at the subtree in this node. Similarly, here it is 8 because this is the max high end point, and we have to put it here. So this will be formula is max between this left part, left max, which is 8, right max 18, and 11. So among these three, 18 is the maximum. We put 18 over here. So 18 is the maximum value rooted at this subtree. Similarly, this is 23, and this is also max of 18, 23, and 19. So this 23. So is this okay? So this is the extra information we are keeping over here. So this is the max field. So how it will help us when we discuss the code of finding the interval search. So again, we have to check the how we can maintain this extra information with the same cost of insertion and delete. So for that, we just need to check the rotation operation, because other than rotation, coloring will not affect, because anyway if we have to insert, we have to do the coloring. So that will not affect in this new thing. Only thing, if we rotate, then this value will be changing, so that we have to take care. So that we can easily verify. That can be done in constant time. Suppose this is a part of the tree, we have some portion hanging over here. Okay, now suppose this is, we want to do the rotation, this is up, this is down. So right rotate, so now this is up, this is down, this is again alpha, beta, gamma. So it will be hanging over here. So there will be no change in alpha, there will be no change in beta, there will be no change in gamma, because we are not disturbing there. Only thing, there will be changes here, because this was having 30, now we have alpha, beta. So we have to check this max here, and then 15. So among this 14, 19 and 15, 19 is the maximum, we put 19 over here. And similarly here, so this was so this is 30, and this is 19, and this is 20. So among this, whichever is the maximum, 30 will put here. So only 2 3 field we need to check. So that will cost us constant time. So this can be handled by the same cost of insert and delete with a log n time. Okay, now go to the code, which is the why we are keeping the max over here. So that will be clear from this interval search. So this is the pseudo code for interval search. So what is the problem? Again, we are recopying. We have some intervals. We are storing this in a red black tree, where the which is keyed as a left end point, and we are putting the extra information, which is the max information of the tree rooted at this. Okay, so yeah, this is the interval search. We have given a tree, so we are taking the root in a x. So x is the root, this is our x, this is the root. Okay, now x may be nil, we may not have any, so or later stage it may be going to the nil node. So we have to return that no, there is no interval which is overlapping with this. Now we want to check whether our interval, query interval I, we have given some interval I, which is left end point, high end point, left and high. We want to check whether x is I is overlapping with x or not. How to do the, how to check that? So this is one condition. Another condition is it is not overlapping actually. So if say how to check it is not overlapping, suppose I is say 2,5 interval. So when x will not overlap with I, if x is completely here or if x is completely here. So if x is completely here means the high of x is yeah. So if high of x is if low of x, low of I is greater than high of x, or low of this interval, low of x. So this is our x. So this means what? This means high of x is less than low of x. So this is the first condition. Okay, that means x is completely in the left part. Then it is not overlapping. Or if x is completely in the right part, in that case what? In that case, this low of x is greater than high of I. That is the second condition. Is this clear? These two conditions will indicate that it is not overlapping. Then only we will go for further search. If it is overlapping, then we will return that, because we are looking for only one interval which is overlapping with this given query interval. So we will only go for the further if it is not overlapping. So or if it is null, there is nobody to search, nobody to check. So when it will not overlap, if it is completely in the left part, in that case the low of I will be greater than, this is high of x, will be greater than high of x, that is this part, or the low of x, this is this point, will be greater than high of I. Then this will be in the right part. If this both, either of this part is this one, so then it is not overlapping, then we have to go for further. So the question is which way we should go? We should go left way or we should go right way? So this we have to determine. So this we will determine by this step. So we check whether left part is null or not. If there are something to search, we have to see. Now consider this one. So if low of I, so we are searching an interval I. Okay. Now if low of I is less than max of left. Okay. Then okay, just a minute, if we take the other way around, if low of I, it's better to take other way around. If low of I is greater than max of left. If low of I is greater than max of left of x, then what will happen? Then will you go for the left part? So here this is max field. This is max of left, some m, max of left. Now we are searching an interval whose low end point is greater than the greater than from the max. So then will you go for the left part? No, no, because in that case we know there will be nobody there which can overlap with left part, because if the low of I is greater than this is the field which is indicating what is the maximum point in this subtree rooted at here. So if we are looking for a interval which is overlap with I, and if low of I is greater than max of left, then there is no question of going for left part, then we will go for the right part. So that is this. So this is the other way we have taken. So if low of I is greater than max, then we will go for the right part, otherwise we will go for the left part. Is this clear? Because if we are looking for an interval which is overlapping with I, now if the max is less than I, low of I, then there is no question of going to the left, because there will be nobody which can overlap with I, because all the interval which will be less than I. The only thing is we have to go for the right part. So that is we will go for the right of x. So this is the pseudo code, and this will ultimately, it will return x. I mean, if we have overlapping over here, then it will return x, or it will return a nil if there is unsuccessful search, if there is no overlapping. Okay, so we'll take a quick example. Suppose we are searching the interval 14 and 16 in this our given set of intervals. So now we start with here. So we'll check whether 14 and 16 is overlapping with this or not, with the root. No, it is not overlapping. So, and it is not nil also. So we have to go for further. So we check the left part. Yeah. So we check the. Just let me erase. Yeah, we check the. This is not overlapping. So we have to go for the. Now 14 is, so we check the left part of this. This is 18. This is 18. Now if I is greater than 18, then we'll not go for the this part, we'll go for the right part. But here I is less than 18. I of low of I is 14, which is less than 18. So we have to go for the left part. So this is our new root. So this is our new root. Then we have to search again. I mean, do the interval search on this root. This is the recursive call. So again we check whether this is overlapping or not. So no, this is not overlapping. So again we have to check with the left part of this. This is 8, but our low of I is 14. So there is no question of going in the right, because there will be nobody in the right which can overlap with this given interval. So we have to go for the left. We have to go for the right part of this tree. So we go for here. This is our new x. So we check again whether this is overlapping with this. Yes, this is overlap. So we return this interval 15 and 18. So we'll return that interval 15. So this is basically a logarithm time, log n time, height of the tree. Now for an unsuccessful search, suppose we are searching a interval which is not there, say for 12 and 14. So we do the same thing. We'll start from the root. It is not overlapping. Then we check left part. So we have to go for the left subtree. Then again we check whether this is overlapping. No. Then again we check this. This is 8. 8 is less than low part. So there is no question of going left. We have to go right. So right, this is our new root. This is, we check whether overlapping or not. No, this is not overlapping. Then again we check 10. 10 is less than the low part. So there is nobody interesting in the right. So we have to go for the left. We have to go for the right. So if you go for the right, there is nil. So we just, when there is nil, we stop. There is no stopping counter, because there is nobody to compare again. So we return that. So this, there is no such interval which is overlapping with this given interval. So in the case, it will take order of log n time, both the cases. Okay. So now the question is, it will take log n time. Now suppose we want to return all the elements. Suppose there are all the so in this code we have written only one interval which is overlapping with this interval. Now suppose there are k intervals which are overlapping with this given interval. So how to return all the k intervals? Any idea? You got my point. We are looking for a overlapping interval which the given query interval I. Now suppose there are k intervals which are overlapping. K is say 2, 3. Now we want to return all of them. We want to get
So
all
we
the.
can do interval search by taking different roots of the tree.
But if we again run the same code, it will hit to the same interval.
Like from below to up, we can go for.
But in that case, how we'll maintain these properties and all these things? Any other idea? Quickly. So if we do the interval search, it will hit to a interval which is overlapping. We are happy. We got the interval. Now we want to get the next interval. I mean, all the k there are k many intervals which are overlapping. We want to get the next interval. How to do that? Because search again, it will hit to the same intervals. Any guess? We delete it. Once we get an interval, we delete it from the tree. High deletion will cost log n time. If you delete this interval which we have get, then if we again, after deletion, if we again search it, then it will get the next interval which is overlapping. Once we get it, delete it, get it, delete it. So in that case, so we'll do the we search the interval, we delete it, and again we'll search, we'll get the next interval, delete it, like this. So Yeah, how much time it will take? It will take k log n time, because the deletion will cost log n time, and again the searching will cost. So this is output sensitive bound. Okay, so this is the interval search. There is a data structure which can take k plus log n. Anyway, we will not discussing that. So anyway, this is the correctness we have already discussed of this. So any question before you stop? So this is what is called data structure augmentation. We are taking an underlying data structure, and then we are maintaining the we are introducing some extra field of information for our purpose, and then we are seeing that that field will help us to do the query in a faster way, and also we have to maintain that field, that extra field, in a same time with the insert and delete. So that is very important. Okay, so thank you very much. Let me stop the recording.